The RMS or root mean square value of a direct current signal is simply the value of the signal itself. This is because the RMS value is defined as the square root of the average of the squared values of the signal over a period of time. For a direct current signal, the value is constant over time, so the average of the squared values is simply the square of the value. Therefore, the RMS value of a direct current signal is equal to the square root of the average of x squared equals the square root of x squared equals x. The constant value of a direct current signal ensures that the average of its squared values is always equal to the square of that value. This is a fundamental property of RMS calculations, and it applies to all signals, regardless of their shape or frequency. For a direct current signal, the average value and the RMS value are always the same because the average value is also simply the value of the signal. For any other type of signal, the RMS value will typically be different from the average value. Now let's delve a bit deeper into why this is the case and explore some examples. Firstly, consider a simple direct current signal of 5 volts. Since the voltage is constant at 5 volts, the square of the voltage is always 25 volts squared. The average of a constant value is simply that value itself. Therefore, the average of the squared voltage is 25 volts squared. Taking the square root of 25 volts squared yields 5 volts, which is the RMS value. This is the same as the original direct current value. Secondly, for a sinusoidal alternating current signal, the RMS value is not the same as the average value. The average value of a symmetrical sine wave over a complete cycle is 0, because the positive and negative areas cancel each other out. However, the RMS value is a measure of the effective voltage or current that delivers the same power to a resistive load as a direct current voltage or current of the same magnitude. The RMS value of a sine wave is equal to the peak value divided by the square root of 2, or approximately 0.707 times the peak value. For example, if a sine wave has a peak voltage of 170 volts, its RMS voltage is approximately 120 volts. Thirdly, consider a square wave that alternates between positive 5 volts and negative 5 volt. The average value over a complete cycle is 0, similar to the sine wave. However, when calculating the RMS value, we square the voltage at each point in time. So, positive 5 volts squared is 25 volts squared, and negative 5 volts squared is also 25 volts squared. The average of these squared values is 25 volts squared, and the square root of 25 volts squared is 5 volts. Therefore, the RMS value of the square wave is 5 volts, which is different from its average value of 0. The relationship between RMS and average values depends heavily on the waveform of the signal. For direct current signals, they are always equal. For alternating current signals, they are generally different, with the RMS value representing the effective value and the average value representing the arithmetic mean over a period. The concept of RMS is essential in electrical engineering for determining power dissipation, voltage and current measurements, and circuit analysis. It allows us to compare the effects of different types of signals in a meaningful way. To further clarify, let's discuss why the average value is 0 for symmetrical alternating current signals. Consider a pure sine wave. For every instant where the voltage is positive, there is a corresponding instant where the voltage is negative, and the magnitudes are equal. When you sum all these instantaneous voltage values over a complete cycle and then divide by the period, the positive and negative contributions cancel each other out, resulting in an average value of 0. This doesn't mean that the signal has no effect. It simply means that the net direct current component is 0. The RMS value, on the other hand, provides a measure of the signal's magnitude that takes into account both the positive and negative portions. By squaring the signal before averaging, we eliminate the negative signs, and the square root restores the units to their original scale. This gives us a value that represents the equivalent direct current voltage or current that would produce the same heating effect in a resistor. Now let's consider a practical example. Imagine you have a 120 volts alternating current outlet in your home. This voltage is the RMS voltage. The peak voltage of the sine wave is actually higher, approximately 170 volts, since 120 volts is roughly 0.707 times the peak voltage. If you were to connect a 10 ohms resistor to this outlet, the power dissipated in the resistor would be calculated using the RMS voltage. The power P is equal to voltage squared divided by resistance, so P equals 120 volts squared divided by 10 ohms, which is 1440 watts. If you mistakenly use the average voltage of 0, you would incorrectly calculate the power dissipation as 0. The RMS value is also used extensively in audio engineering. When measuring the loudness of an audio signal, the RMS value is often used to represent the signal's amplitude. This is because the RMS value correlates well with the perceived loudness of the sound. A higher RMS value corresponds to a louder sound. Similarly, in control systems, the RMS value is used to quantify the magnitude of error signals. A control system aims to maintain a desired output, and any deviation from this output is considered an error. The RMS value of the error signal provides a measure of the overall system performance. A lower RMS error indicates better control. In summary, the RMS value is a crucial concept in electrical engineering and signal processing. It provides a way to quantify the effective magnitude of alternating current signals, and it is essential for calculating power dissipation, measuring signal amplitudes, and analyzing system performance. While the average value of a signal can be 0 for symmetrical alternating current signals, the RMS value provides a meaningful measure of the signal's magnitude that takes into account both positive and negative portions. For direct current signals, the RMS and average values are always the same, as the signal's value is constant over time. Consider another scenario involving a pulse direct current signal. Suppose you have a signal that is 10 volts for 1 millisecond and then 0 volts for 1 millisecond, repeating continuously. The average value of this signal would be 5 volts, calculated as 10 volts asterisk 1 millisecond plus 0 volts asterisk 1 millisecond slash 2 milliseconds. To find the RMS value, we square the signal at each point. So 10 volts squared is 100 volts squared, and 0 volts squared is 0 volts squared. The average of these squared values over the 2 millisecond period is 100 volts squared asterisk 1 millisecond plus 0 volts squared asterisk 1 millisecond slash 2 milliseconds, which equals 50 volts squared. Taking the square root of 50 volts squared gives us approximately 7.7 volts. In this case, the RMS value of 7.7 volts is different from the average value of 5 volts. This example demonstrates that even for non-sinusoidal signals, the RMS and average values can differ significantly. Let's discuss the mathematical basis for RMS calculations in more detail. The RMS value of a continuous signal xt over a time period t is defined as the square root of 1 divided by t times the integral from 0 to t of xt squared dt. In simpler terms, you square the signal at each point in time, find the average of these squared values over the period t, and then take the square root of the result. For a discrete signal, the RMS value is calculated as the square root of 1 divided by n times the sum from I equals 1 to n of x sub I squared, where n is the number of samples. This is equivalent to squaring each sample, finding the average of these squared samples, and then taking the square root. These formulas provide a precise way to calculate the RMS value for both continuous and discrete signals. It is important to note that the RMS value is always a non-negative quantity. This is because we are squaring the signal before averaging, which eliminates any negative signs. The square root then ensures that the result is a positive value representing the magnitude of the signal. Understanding the mathematical basis for RMS calculations is crucial for accurately analyzing signals and designing electrical systems. Now, let's consider the impact of harmonics on the RMS value of a signal. Harmonics are integer multiples of the fundamental frequency of a signal. For example, if a signal has a fundamental frequency of 60 Hz, the second harmonic would be 120 Hz. The third harmonic would be 180 Hz, and so on. The presence of harmonics can significantly affect the RMS value of a signal. Suppose you have a sine wave with a fundamental frequency of 60 Hz and a peak voltage of 100 volts. The RMS voltage of this sine wave is approximately 70.7 volts. Now, suppose you add a third harmonic with a peak voltage of 20 volts. The RMS voltage of the third harmonic is approximately 14.14 volts. To find the overall RMS voltage of the combined signal, you cannot simply add the individual RMS voltages. Instead, you need to square each signal, add the squared values, and then take the square root. In this case, the overall RMS voltage is the square root of 70.7 volts squared plus 14.14 volts squared, which is approximately 72.11 volts. This demonstrates that the presence of harmonics increases the RMS value of the signal. Harmonics can arise from various sources, such as nonlinear loads, switching power supplies, and electronic devices. They can cause problems in electrical systems, such as overheating, voltage distortion, and equipment malfunction. Therefore, it is important to measure and mitigate harmonics to ensure the reliable operation of electrical systems. The RMS value is also used in power system analysis to determine the voltage and current levels in different parts of the grid. Power companies use RMS values to monitor the stability and efficiency of their systems. For example, they might measure the RMS voltage at various substations to ensure that it is within acceptable limits. They also might measure the RMS current flowing through transmission lines to prevent overloading. In addition to voltage and current, the RMS value is also used to measure power. The RMS power is the average power delivered to a load over a period of time. It is calculated as the product of the RMS voltage and the RMS current multiplied by the power factor. The power factor is a measure of the phase difference between the voltage and current. A power factor of 1 indicates that the voltage and current are in phase, while a power factor less than 1 indicates that they are out of phase. A low power factor can lead to increased energy consumption and higher electricity bills. Therefore, power companies often encourage customers to improve their power factor by using power factor correction equipment. Let's consider the difference between true RMS and average responding meters. True RMS meters accurately measure the RMS value of a signal, regardless of its waveform. Average responding meters, on the other hand, measure the average value of a signal and then scale the result to estimate the RMS value. This scaling factor is typically calibrated for sine waves. Therefore, average responding meters can provide inaccurate readings for non-sinusoidal signals. For example, if you measure the RMS voltage of a square wave using an average responding meter, the reading might be significantly different from the actual RMS voltage. True RMS meters are more expensive than average responding meters, but they provide more accurate measurements for a wider range of signals. They are essential for applications where accurate RMS measurements are critical, such as power system analysis, harmonic measurement, and audio engineering. Now let's discuss some common applications of RMS measurements. In audio engineering, the RMS value is used to measure the loudness of audio signals. Audio engineers use RMS meters to adjust the levels of different audio tracks to create a balanced mix. They also use RMS meters to prevent clipping, which occurs when the signal exceeds the maximum allowable level and becomes distorted. In power system analysis, the RMS value is used to measure the voltage and current levels in different parts of the grid. Power companies use RMS meters to monitor the stability and efficiency of their systems. They also use RMS meters to detect and diagnose problems such as voltage sags, voltage swells, and harmonics. In motor control, the RMS value is used to measure the current flowing through the motor windings. Motor controllers use RMS current measurements to protect the motor from overheating and damage. They also use RMS current measurements to optimize the motor's performance. In lighting control, the RMS value is used to measure the voltage and current supplied to the lamp. Lighting controllers use RMS measurements to dim the lamps and conserve energy. They also use RMS measurements to detect and diagnose problems such as lamp failures and ballast malfunctions. In summary, The RMS value is a versatile and essential concept with numerous applications in electrical engineering, signal processing, audio engineering, power system analysis, motor control, and lighting control. It provides a way to quantify the effective magnitude of alternating current signals, and it is essential for calculating power dissipation, measuring signal amplitudes, and analyzing system performance. While the average value of a signal can be zero for symmetrical alternating current signals, the RMS value provides a meaningful measure of the signal's magnitude that takes into account both positive and negative portions. For direct current signals, the RMS and average values are always the same, as the signal's value is constant over time. One more practical consideration is the crest factor. Crest factor is the ratio of the peak value of a waveform to its RMS value. For a pure sine wave, the crest factor is the square root of 2, which is approximately 1.414. For a square wave, the crest factor is 1. For waveforms with sharp peaks or transients, the crest factor can be significantly higher than 1. A high crest factor can cause problems for measuring instruments and power systems. Measuring instruments might not be able to accurately measure waveforms with high crest factors, and power systems might experience voltage distortion and equipment malfunction. It's also important to understand how different types of loads affect the RMS current in a circuit. Resistive loads, such as incandescent light bulbs and heaters, draw a current that is proportional to the voltage. The current and voltage are in phase, and the power factor is 1. Inductive loads, such as motors and transformers, draw current that lags the voltage. The current and voltage are out of phase, and the power factor is less than 1. Capacitive loads, such as capacitors and electronic circuits, draw current that leads the voltage. The current and voltage are out of phase, and the power factor is less than 1. The type of load can significantly affect the RMS current in a circuit. For example, an inductive load will draw more RMS current than a resistive load for the same amount of power. This is because the inductive load requires additional current to establish a magnetic field. Furthermore, consider the impact of PWM or pulse width modulation signals on RMS values. PWM signals are commonly used to control the speed of motors, the brightness of lights, and the power delivered to various devices. A PWM signal is a rectangular wave whose pulse width is varied to control the average voltage delivered to the load. The RMS value of a PWM signal depends on the duty cycle, which is the ratio of the pulse width to the period of the signal. The RMS value of a PWM signal is equal to the voltage times the square root of the duty cycle. For example, if a PWM signal has a voltage of 10 volts and a duty cycle of 50%, the RMS voltage is 10 volts times the square root of 0.5, which is approximately 7.7 volts. PWM signals can be used to efficiently control the power delivered to a load. By varying the duty cycle, the average voltage and current can be adjusted to meet the load's requirements. The RMS value is a key parameter for understanding the effective power delivered by a PWM signal. Lastly, let's address some common misconceptions about RMS values. One common misconception is that the RMS value is the same as the peak value. As we have discussed, the RMS value is a measure of the effective voltage or current, while the peak value is the maximum instantaneous value. For a sine wave, the RMS value is approximately 0.707 times the peak value. Another common misconception is that the RMS value is the same as the average value. As we have discussed, the average value of a symmetrical alternating current signal is 0, while the RMS value is a non-zero quantity that represents the magnitude of the signal. A third misconception is that the RMS value is only applicable to alternating current signals. While the RMS value is commonly used for alternating current signals, it can also be applied to direct current signals and other types of signals. The key is that the RMS value provides a way to quantify the effective magnitude of a signal regardless of its waveform.